All right, the last example of the class. So we have a triangle, it's triangle ABC, and we know the three side lengths in that triangle. And what we're asked to do is solve the triangle, so figure out everything you don't know. Everything you don't know are the measure of the three different angles. Turns out this is another application of the law of cosines. Maybe you know from previous videos that there's three different versions of the law of cosines. The version where you have c squared on the right-hand side of the equation, in which case you have a squared and b squared on the left side, and then you also have this negative 2ab cosine c term in between. You can remember that because it's always negative 2, and then this letter, and then the cosine of this letter. There's another version of it where instead of having c squared on the right-hand side, you have b squared. If you used your b over here, you're left with a and c over on this side that are being squared, and then your term in between would be negative 2ac cosine b. And finally, the last version where you have a squared over on the right-hand side, in which case you have b squared plus c squared on the left side, and your term in between is negative 2bc cosine of a. If I have all three sides of a triangle, there's no way I can use the law of sines, because when you're picturing setting up your law of sines formula, it involves two different angles. And if you don't have any angles off the bat, you'd have at least two unknowns, and you can only use these formulas when you have one unknown. But you could certainly use the law of sines. In fact, you can use any of these three formulas that you want. You want to know capital A? Just use this formula down here. Capital B, use this one. Capital C, use this one. Let me demonstrate. If you're really observant, you might notice that these numbers are the exact same numbers that we ended up with as our example to the previous video. So it should be the case that capital C is equal to 60 degrees. Let's see if that works. If I take this formula right here and I plug in 4, 6, and the square root of 28 in place of A, B, and C, I would have 4 squared plus 6 squared minus 2 times 4 times 6 times the cosine of capital C. Again, I don't know capital C. I figured that out in the previous example, but right now we're assuming we don't know that, is equal to the C squared, so the square root of 28 squared. Let's see what ends up happening. I get 4 squared is 16, 6 squared is 36, minus 4 times 6 is 24, times 2 is 48. So I get minus 48 times the cosine of C, and that's equal to 28, the square root of 28 squared. Be careful here. Common mistake is people take 16 plus 36 minus 48. You can't do that. This 48 is getting multiplied by the cosine of C. You could take 16 plus 36 if you feel like it and figure out that that's 52. And then you have 52 minus 48 times the cosine of C. At any rate, that's equal to 28. What I want to do is figure out capital C, so maybe I can get this cosine of C all by itself. One way to do that would be to subtract 52 from both sides. So negative 48 cosine of C is equal to whatever 28 minus 52 is equal to. Well, 28 minus 52 is negative 24. And now if I divide both sides of the equation by negative 48, I get that the cosine of C is negative 24 over negative 48, which you might recognize reduces to just 1/2. The cosine of C equals 1/2. Let's see, unit circle. The cosine is always the x-coordinate. There's two different spots on my unit circle where the x-coordinate is equal to 1/2. But good news, one of them is down in the fourth quadrant. That's completely irrelevant when we're talking about triangles, right? That's either negative angle measures or angle measures that are more than 270 degrees. That's got nothing to do with triangles. A nice thing about the cosine function is we don't have that same ambiguity that we had with the sine function. There's only one relevant solution to this problem, and it's this angle up here, where the x-coordinate equals 1/2. You might recognize that that happens at 60 degrees. What I'm saying is capital C is just 60 degrees. Oh, of course it was. These were the same numbers that we used in this example where we were told that capital C were 60 degrees. Now that we know capital C, we can go further and figure out capital B and capital A. Again, it's worth pointing out that if this is a test, it's going to be a one-step process. I'll ask you for one of these angles and call it good. And on some of the homework problems, that's what they ask. But there's two problems on the homework where they ask you to completely solve the triangle. So after you figure out capital C, you're supposed to use that information to figure out capital A and capital B. So I want to demonstrate how to do that. Let's find capital A next. To find capital A, it would be this third version of the formula that I'd want to use. That's the only version that has a capital A in it. And using this version of the formula is as easy as just changing the A's, the B's, and the C's into 4s, 6s, and square roots of 28 respectively. Doing so gives you this mess here, which I can simplify because 6 squared is 36 and the square root of 28 squared is just 28 and 4 squared is 16. I want to get A all by itself. Maybe the way I can do that is get cosine of A all by itself. And the way I can do that is get this term and this term over to the right-hand side of the equation. So I have negative 12 square root of 28 cosine of A on the left, and whatever 16 minus 36 minus 28 is equal to on the right. Well, 16 minus 36 is negative 20, and negative 20 minus 28 is equal to negative 48. So I can solve for the cosine of A if I divide both sides of the equation by negative 12 square root of 28. That gives me negative 48 divided by negative 12 square root of 28. And I think that's going to simplify a little bit. Let's see, this negative 12 and part of this negative 48 can cancel out, and that leaves me with 4 divided by the square root of 28, which is a fairly good answer, although you could rationalize the denominator. You can either do that by multiplying the top and the bottom by the square root of 28 right now, or you could recognize that the square root of 28 is the square root of 4 times the square root of 7, and the square root of 4 is just 2. So the square root of 28 is just 2 times the square root of 7, and you could then cancel out the 2 and the 4 to get 2 divided by the square root of 7, which might be a little bit easier to rationalize. You get 2 root 7 over 7 is what the cosine of A is equal to. So that's my answer. Now you're trying to figure out capital A. Capital A is going to be the arc cosine of that thing, 2 root 7 divided by 7. And you're like, ooh, I'm a little bit uncomfortable with that. I remember when you're using these inverse trig functions, you have to be really careful, right? What if this angle capital A is obtuse? Isn't that a problem like it was in the previous section with the law of sines? The answer is no. The arc cosine function is really nice for your purposes, whereas the arc sine function is not. The arc cosine function is restricted to 0 to pi. It gives you an answer in this range. All the possible answers are in that range to begin with, so there's no ambiguity using the arc cosine like there is when you use the arc sine function. What I'm saying is the measure of angle A is the arc cosine of 2 root 7 over 7, and that might be an acute angle, it might be an obtuse angle. You don't have to worry about that at all. There's only one possible solution, unlike in the previous section where there was 2, and this is that possible solution. It's worth pointing out that this looks a little bit different. Arc cosine of 2 root 7 over 7 is not what I came up with up here. Up here, I came up with the arc sine of the square root of 21 over 7. Well, guess what? Those are the exact same. A quick picture proof of that fact is a triangle with side lengths 2 root 7, square root of 21, and 7 is a right triangle. How do I know that? This squared plus this squared equals this squared. This squared is 4 times 7, which is 28. This squared is 21. 21 and 28 is 49, which is exactly this squared. What I'm saying is these three side lengths form a right triangle. And if I think about some angle T down here, I could say that the sine of T, using SOHCAHTOA, again, because this is a right triangle, because this squared plus this squared equals this squared, would be opposite over hypotenuse, so the square root of 21 over 7. If the sine of T is the square root of 21 over 7, then the arc sine of the square root of 21 over 7 is equal to T. And you're like, yeah, so what? Well, look what happens when I look for the cosine of T. Cosine of T is adjacent over hypotenuse, so 2 root 7 over 7. Therefore, I could solve for T by saying T is the arc cosine of 2 root 7 over 7. Whoa, T, it's the same T because they both came from this picture. The arc cosine of 2 root 7 over 7 is the same as the arc sine of the square root of 21 over 7. What I'm saying is the two answers that we've gotten in this video and the previous video for what A are equal to are the exact same number as they should be, since it's the same triangle that I'm solving for. If I lost you there, this is all completely optional. Don't worry about that stuff. Remember, our goal in this video was to figure out capital A, capital B, and capital C. We figured out capital C was 60 degrees. Capital A we just found over here, but be careful because we're using arc cosine. This is in radians. If you want it in degrees, like your homework will, you better multiply it by 180 over pi. And we're still not done because we need capital A, capital B, and capital C. However, when you have two angle measures in a triangle, you really have all three because the sum of the interior angles in a triangle is always 180 degrees. So capital B is just 180 minus 60 minus this number. In other words, 120 degrees minus the arc cosine of 2 root 7 over 7 times 180 over pi. Solving this triangle meant finding capital A, capital B, and capital C, which we now have. So we're done with this example and done with examples for this class.